Okay, okay. Good afternoon, everyone. So today we will have the continuation of the previous class, which is discuss about the regression. We've discussed it before in the bivariate model, just two of variables, which is the salary and also the ROA. We intend to know how much is the ROA have an impact to the salary of CEO. So today we want to uh, evaluate and see the expansion of the models and the methods that we've learned before, which is the regression. Today we will use the more complex form of it, which are the non-linear model and also the multivariate model. It was not different with the previous one, but there is some additional assumption and condition that we need to adjust there. So yeah, hopefully you can continue and follow the idea about the previous meeting, so you didn't lose in the mid of the discussion. So let me start the subject. So the first of all, I will tell you about the nonlinear regression. The nonlinear regression is a key where you tend to see the nonlinear relationship between two variables. Maybe some of you start asking about, is it possible to use the OLS for the nonlinear regression? As I've told you before, that there is a strong assumption that we just can do the linear things in the this type of regression or methods, but actually there is a difference between what I am saying here about the nonlinear with the previous assumption that we've discussed in the class. Here, the nonlinear is in the variable, so we allow that some variable to have a nonlinear relationship. Meanwhile, when we talk about the nonlinear and linearity in the assumption, it was uh, targeted to the parameter. So we never allow the parameter to be nonlinear. It always linear. Nonlinear mean can be a fraction, can be exponential, can be, yeah, another forms or mathematics that is not linear. It was not allowed for the parameter, but for variable we can use the nonlinearity. For the example here, we discuss first about the quadratic relationship. Quadratic relationship is a form where variables can have additional effect respect to the x, or maybe the variable that maybe, yeah, that have more than just a linear effect to the dependent variable itself. For the example here, we have a nonlinear equation, quadratic equation, which is the model is y equal to alpha plus beta 1 x1 plus beta 2 x. This is should be x2 x1 quadrat. So this one is the quadratic form of it, and uh, here we see that the parameter is still linear. It's just non-quadratic here, b1 and b2, sorry, beta 1 and beta 2. Both of them is non-quadratic, but the x1 here, we have two x1. The first one is just linear as usual, and the other one is a quadratic form of the first one. So here the non-linearity is appears, and in the form of the quadratic. So in this condition, uh, we need to address how is the effect. I didn't want you just to regress and say it is low and then you just do a regression of it, but there is no explanation about how you can read and what is the impact of the model itself. Here we need to know first what is the basic impact and basic magnitude when you use a beta without the nonlinearity. As you know that if we just have the y equal to alpha plus beta 1 x1, so it's just a linearity here. It means that if the x1 is increased for 1 point here, x1 is increased for 1 point, then the y should increase depends on the beta value, right? I mean, like if it was 0.5, then if x1 is 1, the beta is 0.5, y will increase 0.5 multiplied by 1, so 0.5 is, and yeah, plus for the alpha, which is constant for every condition of the x1. So we can make it official and formal for the mathematical form by do first difference of the equation when we just have the form of this model. It just consists of the linearity. When we try to see the effects of incremental of the x1 to the y as the dependent variable, we can just do the difference of the y difference by x1. So we will do the difference the y difference by the x1. It will be equal to the beta, because the beta is just the one who have the x1, and then the x1, this is the quadratic form of 1. X1 is 1 because it didn't have a quadratic form. I mean, like, yeah, this is just 1 here. And when we do a differentiate, the 1 will be multiplied by beta and the x1 will lose here. So at the end, it's just the beta. And then we know, if we want to know the effect of x on the y, the effect is beta. That's why the incremental of the x, the y affected by the x is beta. But here, if you have a quadratic form of it, we can see that there is additional information here, which is when x is increased 1 point, how much the y will increase also. We need to do a differentiate to do the same thing, but no, not it's just in the linear model, but also in the quadratic form here. I'll try to. So if we do a differentiate for it, we can see that there is beta 1 as the similar of effect from the x with the previous one, but there is new effect, which is beta 2 multiplied by 2 multiplied by x1. Sorry. So the effect is when you have an x1 here, for the example, when it is increased 1 point, the x1, the y will increase beta 1 plus 2 beta 2 x1. So let's say, let's try to have a good example here. For example, this y is y, and we want to know that alpha is, for example, 10. This is just an example, okay? Beta is 0.2, x, this is 0.1, x1 quadratic. Here, if you want to know how much is the y, for the example, if the x is 1, then the y is 1 multiply 10 multiplied by 0.2 multiplied by 1. Sorry, this one is 1. Let me. Quadratic. So the incremental is now the beta here, and then here multiply by this one. But now if the x is 2, here is 2, then this one is also 2. I know maybe it sounds complicated, but actually when it's 2, the incremental of the model that have a quadratic and positive here, it will increment more than just beta 1, but it's exponential, you know. I mean, like, normally if it's linear, the incremental of 1 from the 1 to the 2, it was 1 additional, right? 1 point additional. The differentiate between 2 and 1 here, it was 1. The beta, the incremental of the y will be depends on beta, but now the incremental is not just depends on beta, but the beta 1 plus 2 multiplied by the beta 2 and depends on the x itself. So if if you see that we have more higher x, for example, this one is 2, the x is 2, the incremental will increase. If you have 1, the incremental is 0.2 multiplied by 2 multiplied by 1 multiplied by 0.1. But now when we have 2 here, the incremental is 0.2, 2, this one is 2. It's so hard if you didn't use the whiteboard. Now the score is around, if we have the first model, the incremental is well, where is this one? The incremental will be 0.2 plus 2 0.1 multiplied by 1. So it was like 0.25. Now the effect is, because this is 0.2, this is 0.1 multiplied by 2 and multiple by x1. Sorry, let's make this one more smaller than. Usually the beta 2 is so small, so make it 0.01, 0.05 for the example. So it will be like 0.3 here. I'm sorry. Let's change the idea. Because yeah, this one is 0.2, 0.2, and this one is 0.1, so 0.05 for example, and we multiply by 2, so it's 0.1 multiplied by 1. And how if the incremental is the x is 2 now, for example, we use this one, it will be 0.2 plus 2 multiplied by 0.05, so it will be 0.1, 0.1 multiplied by 2, berarti the incremental is then 0.4. So the effect of the, what I say, independent variable on the dependent variable now is not constant, not is just beta, but it will be depends on the x value of the base value itself. If we try to identify the x value of its 2, it will be more higher than if we just have 1, and also that's often to the negative value that appears in the x1. So yeah, that's how the effect of the x to the y as the dependent variable. So it was so interesting because if you learn about how, for example, let's talk about the technology adoption. Some people says that younger boy, yeah, they have lately child can also access the technology, but somehow there is a limitation for the child, and you compared to the younger or the older people that already learn in education in the school and the university and something, they will learn more software and become more complex in terms of the technological use. So older people tend to have uh, more knowledge about the technology, so they have better understanding about the technology itself. But at some point, maybe they start tired with technology to learn. The learn curve will be decreased, and they can't even adapt with a new technology anymore. So it's like you have an additional, but somehow the differentiate of the additional things is decreased one by one. So at the end, it was diminishing. It was similar with the economical concept about the utilities. If you remember, you eat the ice cream at the beginning, you get one ice cream, it feels good, you can taste it good, and then you add more, you eat two ice cream, it still feels good. But when you start to eat for the 10th ice cream or maybe more, you will be sick, of course. So it was a diminishing theories of utilities, and if you imagine in terms of the mathematical perspective, it was a condition where, yeah, the utilities increase, but the incremental is decreased one by one. So before the satisfaction is like 10, I get a 10 satisfaction, and somehow when you decrease, when you add more, the satisfaction is maybe still increase 11, but the next one is get down to this 9, 8, 7, and at some point maybe minus. It was the condition where you can make uh, non-linearity, especially for the quadratic. But if you have a condition like the incremental is positive and somehow get negative again, it was there was two turning point. But here I just give you an example about one turning point. If you have a one quadratic there, so it like you keep increase day by day, but somehow the incremental is decreased. So at some point it was no incremental anymore. So that is the idea about the non-linearity regression, especially when we talk about the quadratic relationship here. This is how you do it in the ifuse. You can choose between using the syntax or the general user interface that we already learned in the class also. Here we want learn a lot about the uh, new things. Actually, we already learned about some operation and syntax that we've learned in the previous meeting also. We just here the equation. It was a common one to do an equation, but here we just put a new variable, namely rho sq, which represents the square of the ROE itself, uh, and the new, maybe I just forget that we learned about this before or not, is the syntax of series. Series is something that you can use to create a new model or you new uh, equation, or maybe a new, yeah, variable actually, which can be defined by you using the syntax. So here we just ask the ifuse to create a new series, which is consists of ROA SQ equal to ROA multiplied by 2. So sorry, which is ROA squared. I just forget the, because the cursor is block me. So the ROA square of the and it was the name was ROSQ. So you can choose this one, and after you create the series, you can do the equation here. That was the idea about the nonlinear regression, and then you can just also use the general user interface like usual. So here for the example, we can click the quick and then choose the generate series, and then we can enter the equation that we want to know, and then we put it in there, in the sorry, and then we can click the enter, and after click the enter we can make a regression using the estimate equation menu in the quick also, and we put the variables, which is now we have a new variable, namely ROASQ as the new variable, which consists of the square of the ROA itself. I'll do it in the effusion. Just wait. Okay. So here we want to see how to implement the things that we've learned in before uh, in the PPT. So what we need to do here is try to identify first about the uh, new variable that we want to regress, which is the square of the ROA. So we tend to create a new series or new variable, namely ROA SQ, for example, equal to square of the ROA itself, like this. And then we'll have a new one here, ROA SQ. And then we can do a regression, where is equation, EQSQ, this is the name that I create for it. The function is ls, and then the variable dependent is salary. The independent variable is ROA and ROASQ and C. When we need to click there, we can see that there is a new variable, namely the ROASQ here, not just ROA. The implication will be like this: if the ROA is 1 percentage point, the effect is now 33 $33,000 salary increase, me minus this one is the ROAS cube uh, minus 2 multiple by beta multiple by x or the ROA itself. So it will be 33 plus minus 0.31 multiplied by 2, which is now 628 0.628 multiplied by 1 because the ROA is 1 percentage point. So it will be like around 27 or maybe 26 thousands dollar of the salary. So it will be around that. But if it's increased for the arrow second for the arrow A with the value of 2, for example, 2 percentage point, it will be still the same for the beta 1, but the beta 2 effect is now 0.31 multiplied by 2, which is 0.628 multiplied by 2. So the effects is the negative is become bigger and bigger. It means that the incremental of the beta 1 will be diminished when the ROA is higher and higher. That's why the curve is not linear anymore. It will be like have a U-turn because there is a maximum point for it, and at some point, if the ROA is too big, maybe it will be diminished and get a new negative. Here we ignore the result of the prop first because we just try to identify, but we can see here that it's not significant. Okay, that's all for this. Okay, the second one is about the logarithm relationship. So this is also the nonlinear regression, where previously we talk about the quadratic relationship. Here we use the logarithm, and as you know, here we can do the logarithm is not just in the independent variable but also independent variable, and we can use it, and we'll use it especially in the time series, which will be discussed in the next meeting maybe. But today I want to give you an idea about how we can do a logarithm and what is the implication of it. The logarithm is as simple as we make the simplification of the number, so it can make us make a simplification of the value that we want to regress. For example, if you have like if you have some research previously in the bank topic, you can meet the variable, namely an asset, which is so big. It's like 10 trillion rupiah, 10 million rupiah, and something 10 billion rupiah, and something which have the variation will become so extreme, and then there may be some variation that hard to be captured also. So the idea is we can make it a simple thing. Instead of using asset, usually we use the size, which is the length or logarithm natural of the asset. And the discussion is about how we can interpret the logarithm when we try to do it in the our models or something. The idea is depends on this table, which just show us that the dependent variable when we have a level model which is not locked, like in the first row in the table, y is the y and x is the x. It was the implication is delta x, delta y will increase depends on delta x multiplied by beta. So as simple as we've learned in the linear model, it was the linear model at the end. But when we try to do logarithm in the x, so the incremental of the y will not just depends on beta multiplied by delta with x, but here we tend to identify the effect or the incremental of y by using a percentage. Remember in the class I also discussed about you about the percentage point and percentage. Here we do a percentage. So the incremental of beta, so the incremental of y is equal to beta divided by 100% delta x. For example, if the beta is 0 0.2, so 0 0.2 multiplied by divided by 100, uh, which maybe 2 at the end, 2% multiplied by x. So the interpretation is uh, delta y will increase certain percent point when the delta x increase 1 point, something like that. I mean, like if we back to the, I say in the example, the CEO and the ROA, CEO salary and ROA. Here, for example, so we'll know that the CEO salary will increase certain thousand US dollar when the delta x is increased certain percent. Because what? The delta x now is the logarithm. The delta x now is the logarithm. So we'll use the percents for the x. So the y will increase 1,000 US dollar for example if the x is increased blah 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 percent, something like that. So we didn't use the percentage point of the ROA like in the first interpretation, since we already used log for the x. And how if the log is on the dependent variable or in y? It will be the y increase for certain percent point, sorry, certain percent if the x increase by 0.2 percentage point, because x is ROA and it was percentage point, remember in the class. So the y here is in percent, not percentage point, but here is percentage point because it was the ROA, which is the variable consists of percentage. And then the last one is log, where two of them is log. Then we talk about the percent between the x and the y. So that's how we can read and use the logarithm equation. This is the things that we can do. This is similar like the previous nonlinear regression, which is the quadratic form. In the quadratic form, we already see that we can create a new series, namely ROA square. But here we make a new series, namely the L salary, which is consists of log equal to log salary. Uh, and then after that we can do a regression where we didn't use the salary anymore, but we use the L salary as the logarithm of the salary itself. And then the independence is still the same, the ROA and the C. And the last one is we can also use the general user interface. We'll do it later in the views. I'll give you the video also. Uh, so here you can do by using the quick generate series, and then you write off. Sorry, you shouldn't write the series here. It was just L salary equal to log salary to help you define about the variable that, or maybe a new variable that you want to create there. And then the last one is you can do a regression. So this equation can be regressed by using quick and then estimate equation. You write off the L salary equal L salary ROA and C as the dependent variable and dependent variable in the dialog box of the estimate equation. And then the second one is how we can do the uh, non-linearity for the logarithm. So we can just create a new one like before, series L salary for the variable equal to ROA L salary log of salary. And then we do a regression also, log for the sample equal to ls. Now I've used the L salary variable ROA C. Then we can call the eqlog result. This is the things. So now the coefficient is so small, right? But because this is the ROA is the percentage effect, it's not the ROA percentage point anymore, but this is the effect. So if the ROA increase for like 1 percentage point, the salary will increase 0 point, sorry, 1%, 1%. So ROA increase like our ROA now is 6%, 6% gitu in news, which is increase than previous year, which is 5%. For example, it was the incremental of 1 percentage point. The salary is increased 1%, referred to the beta here. Why percents? Since we already locked the salary, which is previously not locked, it was the $1,000 if you remember, and because we make a lock, it changed to be a percent. The interpretation of this is percent. So, oh, how can it be so small? Because we use lock now, and it was a percent for the interpretation. So that's how we can do it. And I want to show you because the approach of the previously and this one is the same. I want to show you about how we can do it using the GUI. So if you want to do the GUI here, you can do it. I will give you an example for the log, but it's also similar for the square or maybe the quadratic that we've done before. Here I will delete first for two of it. So you can just click quick here and generate series. You can define again our salary equal to log of salary in the bracket and then salary. After you have it, you can click here estimate equation, and then you can write down here our salary as the dependent variable, and then ROA, and then C, enter. It will be the same here, but I've told you before that it won't be included in the work file except you already write the name and then you write down here, so you have the same result like before. Thank you. No, we still continue for the class. So that's all about the non-linearity. I want to introduce you also about the multivariate regression. The multivariate regression is actually not different with the bivariate that we've learned before, but here we need to adjust and give you some new additional assumption and adjusted assumption regarding the assumption that we've discussed before. But here, since I want to use more proper data, which is the data loan. The data loan is data that maybe consists of uh, loan disbursement in the US. It was the loan amounts, and then there also the revenue that the applicants get, and then total employment and whatever that we learned before in the data. But here I want to show you how you can input the data. It was basically the same with the first meeting, and I'll have discussed and show you how to do that in the class. So yes, we have open data loan if you have syntax, and if you're using GUI, you can open the import in the files menu and just choose the uh, import the Excel files, and then yeah, I choose their files and then just next and finish until the last of the dialog box. So here the idea is that we have more than just one variable independent. There is also a variable dependent, the same, just one, of course. But new, we have more than one independent variable, which is x1, x2, and x3. And every of the x have their own beta. So there is beta 1, beta 2, and beta 3. Here, for example, I have the data of the loan amount disbursement, and I have the independent variable to identify how much loan that they can get. If they have some profile, like in the X1 we have the borrower's income, the X2 is the house price itself, and then the X3 is length of employment. And then we can do some regression. Basically, if you do regression in just bivariate, you can see and you can inverse the variable easily and see how can the x is give an impact to the y. It's by doing the covariance of x and y divided by the variance of x. So it was as easy as that. But when we do a multiple regression here, it was consists just it consists more than just one variable, which is x1, x2, and x3. So when you try to do a regression, it's not as simple as before. We'll use the matrix. So it's why the name is econometrics, because we make a matrix at the end. We make a matrix where x1, x2, and x3 will be placed in the matrix itself. It was contain the column is depends on how much the variable, and then the row is the observation that you have for each of variable. It should be a complete observation also. So if you want to do a regress between the x1 and y, and then yeah, you make a regression of x to the y and something like that. So yeah, this is how the multiple regression, multivariate regression actually can be a little bit different with the previous one. And then since we make a differentiate for each of variables separately to compare to the another variable, that's why in the interpretation we need also to assume that the other variable is constant. I mean, if we want to interpret the x1 or beta 1, we should assume that the assumption that beta 2 and beta 3 is constant. So there is no change on the model on the y, on the variable dependent. For example here, beta 1 is the magnitude impact of the x on the y. So when we want to know, it means, and we found that beta 1, it means that how much beta $1,000 in loan value when there is an income increase by 1 point or one by $1,000. So one can be depends on the measurement unit of measurement that you have. Uh, Here I use the $1,000 for the borrowing. Sorry, for the borrower's income. And then the x2 is the house price, and the last one is the loan the labor duration. So but there is a high assumption that we need to assume when we analyze the x1, we assume that the x2 and x3 is remain constant. It is so important because when you do that, the regression basically do a spread approach for every beta. That's why it's not a joint probability. If you do a joint, we do a f test instead of t test. Here usually we will use the t test itself. Okay. In this step, this is the thing that you can do when you want to run a multiple regression, multivariate regression. Actually, the term that we can use is a multivariate again instead of the multiple. We can do an OLS concept, but now the independent variable is not just one variables, but also include the three variable for the example here, like equation ecmul.ls. That was the name. Ecmul.ls is the name. Sorry, this is the name of the equation that we want to run, and then this ls is least square. This is variable dependent loan amount, and this is the independent variable being price, emp, and also c. Apping is the applicant's income, and then emp is what I say here, the employment period, if I'm not wrong, and price is the house price that you want to know. This is the general user interface. We can also use the estimate equation quick and estimate equation dialog for the loan amount, apping, and price emp. So that was. And then for the regression, there is some assumption that we. Okay, for the multiple regression, I've told you that we will use another data. So this one, because I already asked you to create what I say directory which include all of the data. So you download in the OneDrive and then you copy it in your drive. This is the data. The data is namely data saham, if I'm not wrong. If wrong, you can get a notification after this. I just forget about this. Oh yeah, it's wrong there. Oh, sorry, I made I make a mistake. Wait, I haven't copied the data also, so I need to copy this one. I don't know why. Let me copy. You just download, okay? This is the copy, but I put it here in one of my one, and then I can click here. It can be run here. Just click next, finish. So this is a new data, but I have more variables, so I can expand the idea. And the idea about the multivariate regression, sometimes we need to have more observation than before. Just to make it so real, I use the new variable here and a new data here. So in terms of doing the regression, we can just do an equation here, and then we do the eq mul. I give the name ls, and the variable is, if you refer to the ppt, it was the loan amt, and then price apping, price emp and c, and then you can see the result. This one, the result. So we can see here that there is more than just one variable here. The apping, the price, and emp significantly affect the loan amount. It the 5%, except for the emp, it's significant 10%. And I've told you before how to do a heteroscedasticity test. You can just click here, the residual. You can check the heteroscedasticity and so on. But I won't tell you a lot about the assumption. We can just read here that the apping is, if the apping, this is the apping is income of the borrowers, which is in $1,000 US, and this one is also in $1,000 US. So the interpretation is, if the income is increased for like $1,000 US multiplied by this one, so it's around 67 US dollar, 67 US dollar increase. The loan amount, sorry, the income of the borrower is increased for $1,000 US. The loan amount will increase for like $67 maybe. So it's just small incremental due to the apping. But for the price, if the price is increased for $1,000 US, then the loan amount will increase for like 1 multiplied by 0.5, so 0.5 $1,000 US, or maybe 500 US dollar. So it was the interpretation of it, and we when we interpret the effect of price to the loan amount, we assume that apping and emp is stagnant. And then I will try to do this. You can also try to make. So the idea about how to see the multicollinearity, I forgot to tell you in the PPT, but here I want to show you. We can group here. I create a group, namely some variables that we want to use, loan amount, apping, price, emp, and then we make a correlation table. So I group it, namely regvar, which consists of loan amount, apping, price, and emp. And after that, I ask you to see the correlation of the group. If there is a correlation, especially about the independent variable, maybe we should drop the loan amount. We just ignore it. We focus on this one. If there is more than 0.8, then there is multicollinearity, and we need to drop one of it. But here, for the price amount and loan amount, we can ignore it because this one is the dependent variable and the prohibited one is the independent correlation. But independent, it's between the independent and dependent is okay, something like that. So this is the multicollinearity test uh, for the multivariation. And then should I tell you something again for this one? Yeah, I guess enough. Oh yeah, I need to do it in GUI also. So if you want to do it through the GUI, you can just let's start from the beginning then. I'll just do the import here, import file, and then I open that alone. I just do finish for make it easier, and then after that I can do a quick estimate equation. Then I write down the variables dependent, independent, independent. After that I click OK. The result is appear here. You can interpret, and if you want to make a group, you can click the variable one by one here. For example, this is the I ignore the loan amount for now. For example, FPP Inc. and then the price, and then the EMP. Where is EMP? Here, and then we make it open as group. Here as a group, you can click the correlation, cross correlation, for example. Oh, sorry, I wrong. Here, this is the same. No. This one. I just forget about it. This one. So you can see, you can find the same result like before. I just dropped the loan amount because it was the dependent. It's my mistake before. So it's the same idea. And here the group is not be safe. You need to use the name here. Same to this one. If you want to put this, you set the EQ mul to give the same name. This one is recvar. It will be appears here also recvar ecmul. So it will be the same, totally the same. So this for the try. Need to care. The first one is the information about the as assumption. The A1 and A2 assumption 1 and assumption 2, there's no difference between it. Where the A1 here, the model is still same linear, but then we can have more than one, just one independent variable. The second one is also it was a random sample. You need to ensure that you have a sample, a random sample. Now the third one, you should ensure that there is no perfectly correlated between the independent variables. So you have a variation in independent variables. For example, the variables should be have some value. You can't regress the variable independent that is all is 0 or maybe all is 1, all is the same value. It won't be it will be hard to be and impossible to regress. In STATA you will see that there is a correlated notification, so the result won't be appear there. And then for the ifs you can't even run because they will have a near singular matrix where the correlation or the variation between one or two variables is just so similar and so high, something like that. And then uh, we need to ensure also that the independent variable is not perfectly correlated with the other independent variable, or it can be regressed. So this is the assumption that we need to ensure for the third one. And then there is a major distinctive between the OLS assumption and Bayes-Fred and the multivariate assumption, especially for the fourth assumption, where we need to assume that the error of u must have an average value for equal to 0. Before this, we just need to ensure that uh, the the expected residual or expected error, expected u, is not equal to 0, and for each of x value that maybe appear. For example, if the x is just arrow A is 0, 30%, 3%, and 5%, both of them need to have the equal to 0 and the expected return. But here, as we know that we have more than just one variable, so we need to ensure that expected error is still equal to 0 respect to every independent variable. So In terms of the borrower income, for the example, we have the two thousands, 20,000 and 10,000 US dollar should have the same expected residue equal to zero. Both of them should have the same one, because if not, we knew that we have an error that is not equal to zero. We've discussed it before that this is the the most important part of the OLS, where we can't ensure that there is no error, but at least we provide that at the average, at the aggregation, error should be zero in terms of the expected return, expected value of it. And then sometimes, the since we have some variables, there is some condition that maybe the average error is not zero. Why can it happen? There's three, at least this three is the most common reason why maybe the expected error is not equal to zero. The first one is omitting relevant variable. So it can be so important for us to not forget the relevant variables. So if you just want to know, for example, here we have three variables, which is borrower income, and then the well, I forget the price, and also the EMP. But we just want to know about the effect of borrower income to the loan amount. Then should we didn't input the rest of two variables? I mean, like the price and then the EMP. No, we should still input it, because it will it will give an effect to y. And if we didn't input in the model, it will be on u. It will be the error. We've learned before that residual error u is the value which content of all variables that is not in the model, that maybe affect the y. That's why we need to ensure that it was still in the model, and somehow the u is clean from the relevant variables. If we didn't include those variable in the model and we leave it in the u will have not equal to zero. It will be not equal to zero, and at the end, it didn't fulfill this assumption, and maybe can lead to bias also in the properties. That's why if you open some journal and article paper, you will see there is a control variable, which is important to ensure that the model is good enough. You didn't analyze those variables because it's just a control variable, but you put it in the model to ensure that the model is good enough. So control variable basically same with the independent variable, but it's just focused on, we just put those variable to ensure that we identify relevant variable for the y, for the dependent variable. Even we didn't try to analyze that one. That's why we call it control variable. So we ensure by if there is some possibilities that where the expected residual is not equal to zero, just try to identify new variables and put it in the model. That's why also when you try to do a final thesis for the bachelor degree, for example, you need to search for what I say uh, relevant journal, right? I mean, like you need to find your reference, your your main journal as your reference, and paper in the journal, a quality journal, high quality journal, which can be a reference for you to do the bachelor thesis. It can help you to identify the model, because in the regression you can't just do a regression without an idea about what you want to learn and what is the independent variable and the relevant variables. Because if you didn't put the relevant variables, it will be omitted and you have an expected residual equal to zero at the end. So this is the first keyword. And then there's also some uh, effect like a simultaneity, where the dependent variable may be affected by the by the independent variable, but at the same time the x also affected by the y. It can be a simultaneity, or maybe x1 and x2 is related to each other. X1 affect the x2 and x2 affect the x1. It can the effect can enter between both of them and then destruct the effect of the y itself, and make the residual expected the residual is not equal to zero anymore. That's why you need to ensure that uh, the simultaneity is not there. So simultaneity is like two variables who have a relationship with each other. it was prohibited because yeah, that's why the name is the variable independent, because we need to have these two variable or three variable is exactly independent and not rely on the other variable in the model itself. And then the third one is measurement error, where one or more independent variables are calculated using the error. Maybe there's some relevant variables that is not included in the model, which is similar with the omitting relevant variable, but somehow the independent variable that we already put it in, it was the effect of the omitted one. It's a little bit hard, but we'll not focus on it for now to make it easier for you. And then the next assumption that we need to ensure here also the homoscedasticity. We've learned before that there is a condition where uh, you can face homoscedasticity problem, heteroscedasticity problem where the variance is not constant. You need to ensure the variance is constant, and now it's not just respect to one x, but now we have more than one x. So whatever the x is there, the variance should constant at the same level. So it was best variable based model from the LS, and there is two relevant some two reasons why the variables is not significant, or maybe the variance is not constant. There is two reasons. The first one is you didn't include relevant variables. Also, maybe you include irrelevant variables. So you just, because previously we learned that you can't reject or didn't include the relevant. You just put every variables that you want to the model. Is it good? No, because if you include too much variables and it's not relevant, the variance will increase. It's not as simple, as small as you can, and it won't be constant. That's why you need to choose and do it wisely, which variables that maybe have a positive impact and relevant for the dependent variables. So if you didn't put something, uh, it can be break the A4 assumption. But if you put too much and something that is not important anymore, it can break the A5. So choose it wisely between both of them. And the last one is multicollinearity, where you see that the correlation between two or three variables independent have a high correlation. The rule of thumb is correlation shouldn't be more than 0.8. So you can like make a correlation table or something. Uh, but if it's more than 0.8, then there is maybe a multicollinearity. Multicollinearity affect the effect of the x and y, sorry, the x1 and x2 for the example on y. If they have a high correlation, the effect on the y will be biased. I mean, well, not biased, will not be clear for us, because those effect jointly together affect the y. And yeah, there's also a simple question: why we put two variables that have a similar effect to the y and the high correlation between them and y? So yeah, the option is just you can choose to drop one of them actually. And about heteroscedasticity, we'll learn later. We can use the standardized idea about the the variant, so you didn't have a problem anymore. So that's all about the class, guys. I wish you can learn from this. As I've told you, this is not the end. This is not the main discussion, but I give you this supplement to give you a perspective about the regression itself. Next week, I will enter the time series regression, so it's better to yeah just follow this meeting and the previous discussion also, because it can help you to really easier your lesson in the next meeting. So that's all maybe for me for these meetings. Thank you very much. See you in the class in next week. I wish next week we can do offline again, so it will be better for us to do a discussion there, because it will be a time set and it will be so important for you. Thank you very much, guys. See you.